This is to develop your skills that you can bring to your main tracks. So when you apply to those, you'll be able to handle a lot more complexity. You'll be able to evaluate your code. You'll be able to understand what's going on underneath the hood of something like Redux. So I think take that energy and keep it going. You want to have that when you get to sit down and build something, that it's you have that enthusiasm. Yeah, if you could, I like CS because I can avoid applying for jobs if you're working on algorithms. I think that's okay to do right now. I actually think it's very worth it to spend time to focus on studying these algorithms. If you split your attention too much, you're not going to be effective at applying for jobs. You're not going to be effective at learning these algorithms. So I think it's better to focus for the most part. If you want to take a break and do some research, I think that's fine. But going to like job sites like monster.com or whatever and just clicking like apply, that doesn't really do much. I don't think any of those really turn into very much. The reason they're if it's so easy, then everyone is doing it. And if everyone is doing it, you're probably not going to get much out of there. Better to focus on algorithms, study, be able to demonstrate your expertise, and then make focused connections, right? Start reaching out to people, reaching out to your dream companies, reaching out to hiring managers, trying to reach out to your personal networks, and try to get some warm leads. Those are the things that end up paying off in the long run. Okay, one, getting stuck on correctly applying recursion to the rock, paper, scissors problem. Yeah, that is a rock, paper, scissors is a good problem to test recursion. I have had some problems like that show up in job interviews. So if you feel good about those problems, I think you can feel confident in your ability to do recursion. Let's see, what was one problem I had in an actual whiteboard? I think it was, I think the game is Mastermind. I forget what it is, but I was recursively building like some all of the possible solutions to solve this game. I don't remember exactly, but it was something like that, very similar to the rock, paper, scissors game. The stock price. Okay, let me share my screen. So if we're recording, we can get all of this on camera as well, so people can follow along. The stock price problem was super tough. I think the stock price problem is, like a lot of problems, the toughest part is to understand the problem. Like, what is this thing asking for? What does this array of numbers mean? And how do I go about it? Once you get past step one, if you do understand what the problem is asking for, then the algorithm is fairly straightforward. But I agree that it is tough upon reading the problem, especially if you don't have a background in stocks or finance to really understand what the problem is asking for. Like, for example, I didn't really know what shorting was when I first came across that problem, but I was able to figure out what it was asking for just by looking at the tests, by reading it over a couple of times. And then I think it's pretty straightforward. Falling behind is tough. I know that again, like life is going on, and it can definitely catch up with you. You're not sunk. I would say get through sorting. Try to get through at least the first two problems of this algorithm sprint, and you should be okay for the sprint challenge tomorrow. Let's see. Pair programming, yeah. Second pair programming. And this is why I think attendance is good too. Like all of the fear that you have, the blank page uncertainty, the things that have you falling behind. You're not the only one, and probably not the only one in your stand-up group as well. Your TLs, a lot of them some of them are students as well and part-time, so they definitely know your struggle. They can working at full-time TLs and then part-time students, they can definitely relate to this feeling of not having enough time and just work with no break. So you know, you're not alone here. That's make use of the resources you have. Make use of the community. Make use of your peers, your TLs, your SLs, your instructors. These channels you have to ask questions, and that's how to get the most out of your Lambda School experience. Yeah, these breakthroughs that Rowan's is describing. This happens from tough problems, right? When you're struggling and you're smashing your head against that keyboard over and over and over again, and all of a sudden, like poof, it like clicks, it pops, and now you get it. Now you get it. I've had similar experiences with things like graphs. Like graphs is a subject I struggled with a lot. And I just didn't get it. I just didn't get it. And I don't know. I just kept struggling with it, but one day it clicked. And now I feel like graphs are one of my strongest subjects. So, you know, just keep at it. Don't give up, and you'll figure these things out. Yes, Michael, you're right. You're right. And that's why I say that understanding the problem is going to be the hardest step. If you understand the problem, if you understand the parameters, if you understand the requirements, if you understand the inputs, if you understand the outputs, if you understand all of these things, the plan is usually pretty straightforward. If you come up with a good plan, the code is usually very straightforward. And if you have a good, clean solution, a well-organized solution, it's easy to review and make improvements. But it all starts from that step one, understanding the problem. Especially for problems like this, for problems like these eating cookies, understanding the problem, understanding what it's asking for, because there's some of these, like, there's not really any parallels to real life. Like, how many ways can I eat 10 cookies? 274? Like, what does that even mean? It takes some time to wrap your head around it. So I agree that understanding the problem is the hardest part. We don't intentionally make them unclear, but we are intentionally not writing every single little detail out and to make it easy, right? Because we know this is the hard part. Also, you know, if you wrote everything out, there's another challenge, which is parsing through documentation. And we know if there's too much writing, then people just don't read it. We don't want to repeat ourselves because that leads to desyncs. So yes, this is absolutely a part of the challenge. And we hope that the parts that are unclear, that this will push you to practice asking questions, asking for clarifications, reading, rereading, looking through every resource you have, including the spec, including the code, including the tests. And you should, we know all the information is here. It is possible to solve it, right? We've had generations, many cohorts of Lambda School students have gone through this. So we know all the information is there. We know it's sufficient, but that doesn't mean it's easy. By no means does that mean it's easy. If I show a brute force solution, can you get a non-brute force solution to the stock price problem? So today I'm planning to go through the cookies problem. If you have a solution for the you have a solution for the stock prices, you can ask your TL, and your TL has the Lambda solution, which they can share with you to if you want to see the accepted or the Lambda School solution. I don't want to say it's the most efficient because ours are not, our solutions, they work, they pass the tests, but I do not make the claim that they are optimal. In some cases, we know they're actually not optimal, but they're working solutions. So yeah, ask your TL, and they should be able to provide you with that. Okay, yeah, we'll talk about how to approach solving cookies, because again, I think this is the most mind-boggling. This is I want to walk. I'm not just going to type up the code, but I'm going to try to simulate, and it's a little bit fake because I've solved this before, but I'm going to kind of walk through what my process was to solve. See, you'll see how a real life, professional computer scientist goes about solving these problems. It may be less scientific than you actually think, but in that way, anyway, I'm getting ahead of myself. You can look at the cookie solution. If you solve the cookie problem, you can ask your TL to see the solution, and they should be able to show provide it for you. But after you have a solution, to make sure that you at least give it an attempt. But then you can see, yeah, how we at Lambda School do it. Okay, let's jump in. So our problem in question and I didn't forget about these Slido questions. We will for sure talk about this, but first I'll drop this link too in case anyone wants to add some new questions. All right. So eating cookies. We're going to go through the Ooper process again. So step 1, understand the problem. Cookie Monster can eat either 0, 1, 2, or 3 cookies at a time. If he were given a jar of cookies with n cookies inside of it, how many ways could he eat all n cookies in the cookie jar? Your job is to implement a function, eating cookies, that counts the number of possible ways that Cookie Monster can eat all of the cookies in the jar. For example, for a jar of cookies with n equals 3, there are 4 possible ways for Cookie Monster to eat all the cookies inside of it. So he can eat 1 cookie 3 times, 1 cookie then 2 cookies, 2 cookies then 1 cookie, or 3 cookies all at once. Thus, eating cookies 3 should return an answer of 4. Okay, that's confusing. But let's see if it'll become clear if we keep reading. For this problem, there's a test. Okay, so we have a test file that we can look at for small inputs, and then there's a separate test for large inputs. Okay, I got it. This is about optimizations. This is how to run tests. Cool, that could help. We have some hints. Okay, so recursion, that's a useful hint. How many ways are there to eat 0 cookies? I'm not sure yet. How about a negative number of cookies? I don't think we can have a negative number of cookies, so that's my guess for that. Once we've established the base case, how can you recursively call your function so that you move towards one or more of these base cases, okay? And performance optimizations, caching and memoization might come in handy. Cool. Okay, so let's look at our code. Let's see what we've got provided for the code. We have this eating cookies, we have an optional cache value, and then we have this main function. Maybe we can try running this, although I don't think it will do anything. And Python 3, eating cookies. What was our test? 3 should return 4. There are none ways from Cookie Monster to eat 3 cookies. Okay, so that's obviously not working yet. Let's look at our tests. Okay, our tests are, this tells us a little bit more. This tells us that we had this question here. How many ways are there to eat 0 cookies? Well, this tells us there is 1 way to eat 0 cookies. Now, I know this is something that people get hung up on. It happens every time. They say, well, if you can eat 0 cookies, isn't there an infinite way to eat anything, right? Because you can eat 1 cookie, like 001, 0001, 0000001, and so on, right? You can eat 0 cookies an infinite number of times and then eat 1 cookie. That may be true, but the problem we're giving, the problem that's defined, says that there is 1 way to eat 0 cookies. There's 1 way to eat 1 cookie. So this is just telling us how the problem is defined, right? It's similar to the factorial problem that we looked at yesterday, where factorial of 0 equals 1. This is just the problem definition that we're starting from. So we accept by this definition that there's 1 way to eat 0 cookies, and beyond that, we don't really eat 0 cookies anymore. So yes, even though it's a little bit unclear, and I got confused by this too, but by looking at the tests, we can understand how the problem definition works. Where was 1 way to eat 1 cookie given? Here in the tests. There's 1 way to eat 1 cookie. To me, that makes sense because when I look at this, because I think I can eat 1 cookie and then I've eaten 1 cookie, right? That's our only option. There's 2 ways to eat 2 cookies. Okay, I think I understand that. Let me test this out. So I'm going to, we'll test this out like this. In the README, draw the out how to eat the 3 cookies. Yes. What I want to, the process I want to go through is going to be from this how to solve it. I think I understand the problem. I don't have a total understanding of it yet. I'm still a little bit confused. I'm going to try to figure this out. But what I want to do is I want to try some of these steps. So what I'm going to do is I'm going to make a list. I'm going to do some guessing and checking. I'm going to draw some pictures. I'm going to look for a pattern. I'm going to try to use a model. I'm going to try to work backwards, be creative, all of these steps to see if I come to something. Now, I know a lot of students get really upset when we say, you know, a big part of this is going to be guessing. Like, how do I solve these problems? Well, first you can start off by guessing. Then students say, well, guessing isn't real. Guessing isn't real science, right? Tell me how I solve it. Well, first start off with a guess. You know, it doesn't sound scientific, but this is actually a big part of what real science is, right? There's a whole scientific method around this. You come up with a hypothesis, which is basically a guess. You come up with a systematic way to test it, and then you validate your results or you discard them if you prove them wrong. So guessing is, even though it doesn't sound like a valid solution, it totally is. And again, this is my approach for a lot of these algorithms too. Yes, educated guessing. But if you don't have an educated guess, you can start from an uneducated guess, and then you'll learn a little bit from that. And now your guesses will become more and more educated, right? It's a process. It's a process. So let's see. Let's start from 0, 1. I'm going to start by drawing it out. I'm going to start by making a list and seeing if I can figure out how all of these things work. So for 1 cookie, I think it's pretty easy. There's 1 way to eat 1 cookie. That makes sense to me. How about 2 cookies? I think that's there. This makes sense. I can eat one and one, or I can eat 2 cookies, right? I don't think there are any other combinations. For 3 cookies, I remember in the spec it said that there are 4 ways to eat those 3 cookies. Let's see if I remember them. So I can eat 1, 2, 3, 4. I can eat, 3 cookies. I can eat 1, 2, 3. I can eat 2 and 1. I can eat 1 and 2, or I can eat 3. Okay, 1, 2, 3, 4. That's 4 total ways. Okay, let me see if I can solve 4. We don't have a result for 4, so I don't necessarily have a way to check this, but I'm going to try it out and then see if I can get 5 and get 13. So 4 cookies. How many ways can I eat 4 cookies? Well, I know I can eat 1, 2, 3, 4. That's fine. I can eat 2, 1, 1. Okay, I can eat 2 and 2. I can eat 3 and 1. What else? I can eat 1, 2, 1. I can eat 1, 1, 2. I can eat 1 and 3. 1, 2, 3, 4, 5, 6, 7. So I think that's 7. I don't know if this is correct yet, but I think this looks good to me. So I'm going to try 5 and see if I get 13. Okay, so how many ways are there to eat 5 cookies? I can eat 1, 2, 3, 4, 5. And already I'm starting to feel a pattern in my head. I'm already starting to feel a pattern. Okay, so I do all 1s. Then I'll put a 2, 1, 1, 1. And then I'm going to slide that 2 over. So I'm going to go 1, 2, 1, 1. 1, 1, 2, 1. Oops, 2, 1. 1, 1, 1, 2. All right, now I'm going to do the same thing with a 3. So 3, 1, 1. 1, 3, 1. 1, 1, 3. Okay, I think I also need to do a 2, 2, 1 and 2, 2, 2, 1, 2, 1, 1, 2. And then I think I also need to do 3, 2, 3, 2, and 2, 3. Okay, is that, did I cover everything? How many is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Cool, so I got 13. So I feel like I'm on the right track here. This gives me confidence that my 4 is correct. Even though I'm not 100% sure, this gives me confidence that my 4 is correct. Line 34, did I miss one? Yes, thank you. 1, 2, 1, 2, 2. Okay. I don't know. I don't think I'm gonna brute force this 10. I don't think I'm gonna solve this, but maybe I can work with this to see if I can figure out a pattern just from what we have here. Okay. So what is the pattern here? What was I doing? What was I doing? Well, what I was thinking in my head is that, well, I can start from all ones. I know always that there's going to be a solution that's all ones. Like, and then I can replace one of those double ones with a two, and then I slide it over. I can then I replace three of those ones with the three. I slide that over. I know anytime I have a double one, I can replace that with a two. Okay, but that seems like a very complicated algorithm. Is there a better way? Is there a better way for me to think about this? If I look at my hints again, if I look at the hints again of the spec, what is the base case that we want the recursive function to stop recursing on? How many ways are there to eat zero cookies? What about a negative number of cookies? I wonder if I can figure that out. So one is going to be one, right? Two is going to be two. Three is going to be four. 7 and 13. Okay, so let's see. I think that's cookie of one is one. 1, 2, 3, 4, 5. 2, 3, 4, 5. And cookie of 0 is also 1. This was 2, right? This was 4. This was 7. This was 13. So I also noticed that, so for this 4, right? So for this one, I had all of these things, everything here. If I wanted to turn this into a 5, I could take this and just throw a 1 in front of them, right? I can throw a 1 in front of all of these. 1, 1, 1, 1, 1. And this works, right? This is all of the solutions I have starting with 1. I also noticed that if I take these, I can take all of these and put a 2 in front of them. So this is all the ways I can do 3, right? So I can put a 2 in front of all of these, and these work. And what about all the ones starting with 3? I can also do 3 and then put 3s in front of each of these. Right, so these are all of our things starting with 1, all of our things starting with 2, and all of our things starting with 3. This is where the list comes in handy, because you can rearrange them into some other order that might give you some insight. So like if I put all of the 1s in front of everything, and all of the 3s together, all the 2s together, I can start to see this extra pattern where these ones look very similar to this, except for with the 1 in front of them, right? Like here's my 1, 2, 2. Here's my 2, 2, my 1, 3, 1. 1, 3, 1, 1, 2, 1, and 1, 1, 3. So here I can see that I can take all of these and throw a 1 in front of them. I can take all of these and throw a 2 in front of them, and I can take all of these and throw a 3 in front of them, right? And that comes, and it turns out it looks like I have all of the solutions. I don't think there's any other way to look at the solution. So now I think now we're getting to the crux of the pattern. Like I'm starting to see it, right? For people who are visual, like me, sometimes seeing lists will help me see the pattern. And once you see the pattern, I can see, okay, so now that I have all of these, I can realize that that it's going to be, I take all of the solutions that were 1 less and I put a 1 in front of them. I take all the solutions that are 2 less and I put a 2 in front of them. And I take the solutions that are 3 less and I put a 3 in front of them. And that should give me every single possibility. So that's my guess. Yeah. That's so, Michael, now I can start to see, oh, okay. So the number of ways that I can build 5 is all of the ways that I can build 4 with the 1 in front, all the ways I can build 3 with the 2 in front, all the ways I can build 2 with the 2 in front. So the total number should be this plus this plus this. And that sounds very, very similar to a problem we did yesterday, right? It sounds very close to Fibonacci, where we sum up all of the previous and the 2 previous, except for now we also have the 3 previous. So let's test out that hypothesis. So we have, Fibonacci. That's a funny word. I hadn't heard that before, but yes, I do think it is very similar to that. So let me open up my cookie file. I think I actually have cookies open already. Okay, so what I want to do is, here's my plan. Add all the n-1 combinations with 1 in front. Add all the n-2 combinations, 2 in front. Add all the n-3 combinations, 3 in front. Okay, and now I can try to implement this. So what is our base case? Our base case, we can start just like we did before. We can start building it up brute force. So if n equals 0, return 1. If n equals 1, return 1. If n equals 2, return 3. Wait, 2 is 3, right? Yes. Oh, wait, no, 2 is 2. 2 is 2. If n equals 3, return 4. If n equals 4, return 7. If n equals 5, return 13. Okay, and let me test if this works. So 13 is 7 plus 4 plus 2. 4 plus 2 is 6. 6 plus 7 is 13. Yes. 4 plus 2 plus 1 is 2 plus 1 is 3. 3 plus 4 is 7. Cool. 4 is 2 plus 1 plus 1. Yep, that looks good. 2 is 1 plus 1 plus 0, I guess. And we're down to our base cases. So far so good. So far so good. Let's say else return eating cookies of n-1 plus 1, 2, 3. E plus n-2, n-3. All right, so let's test our function. I know that we have the test files, but I want to actually just try this first before I run it in the test files. Eating cookies of, what was it, 5. All right, this is still brute force. Eating cookies of 10. Let's see what that gives us. 274. Cool. So that gives me confidence that we're on the right track. Now, I don't think this will work for 50, or we can try it for 50. But actually, I already know it's not going to work because Fibonacci of 40 didn't work. So this should take a very, very long time. So now that I feel like our regular function is working, we can try working on this down. We can try implementing the cache. Before we implement the cache, and I guess we can eliminate some of these, right? Because we only need 1, 2, 3 for our base case. Did we count for a negative? I don't know, a negative number of cookies. I feel like it's impossible to have a negative number of cookies. So maybe we can say if n is less than 0, return 0. But I feel like there should never be a negative number of, like, how do you even have a negative number of cookies, right? Does that mean, I don't know. That's maybe a philosophical question. Somebody owes me cookies. Somebody takes cookies out of my stomach. All right. Are there any questions about this before we implement the cache? Cookie Monster has a cookie debt. Cookie debt. Yeah. Okay. Maybe we're getting into economics and philosophy and other things like that. Okay. I'm looking through these questions. I think that there's none on explicit cookies, so we'll finish up this problem first. Okay. So let's add a cache. Let's add a cache. So we can pass in a cache like this. We can say if cache is none, cache equals. We can pre-populate our cache with 0, 1, 1, 1, 1, 2, 2, 2. Then I think we can actually get rid of these. If n equals 0, return 0, else, or else if n not in cache, cache of n equals, we have our solution here. And then we can return, or I guess we can do elif and not in cache. Then return cache of n. We know we're guaranteed to have this. Okay, so let's try this. Let's try this. Eating cookies, we'll try with 10 first. 274, looks good. And we'll try 50. Okay, so our cache is still not working. Why is our cache still not working? Cache equals 0, 1, 2. If n is not in, what are we doing here? I need to add it to line 17.2. Cache of n, if n is not in cache, past, oh, you're right. Yes, thank you. Thank you, thank you, thank you. Cache, cache, cache. Eating cookies of 50. Okay, we got a solution pretty quickly. Is it the same solution? Yes, looks like it is. 10562230626642. Awesome, looks great. We can also try, okay, so this thing is actually pushing in a cache, a different kind of cache. This is using an array cache, which I guess works as well. And it actually works the same since we're just indexing by sequential integers. So maybe we can do something like this. Is what was it? 1, 1, 2, 1, 1, 2. Eating cookies of 50. See if it still works. List index out of range. Well, let's try running the test, because I think this is how the tests are run. Python 3 test eating cookies is not working. Cache equals none. How are we doing this? Print and see what's going on here. Okay. So, because we did in, if we did in, so we need to do elif and not in. So we say cache of n, or how is it populating it? Oh, if cache of n equals 0. I think that's right. No. Okay, I'm looking at this. I'm looking at the solution code too, and I think the solution code is here's what the solution says. So it looks like the cache here is being redefined as a dictionary. Um, so I don't know what's going on with this test. Now that I actually look at it a bit closer, I don't know why this cache is passing in an array and this solution is rebuilding it as a dictionary. I actually like this solution better. So to me, this cache is a little bit weird. So I'm just going to stick with my old solution because I like it better. And I think, I wonder if this will work. This does not work. I saw someone talk about how they were redefining this cache. So I'm actually going to do this too. I'm just going to get rid of this built-in cache. Okay, and it works, and it works. So there you go. Yeah, I think using a list as a cache is weird as well. I like using the dictionary better. I think it's slightly more efficient to use an array, but not really. You'll get when you get to hash tables, you'll see that dictionaries are actually just arrays underneath the hood with a slightly different method of indexing. So this is still pretty efficient. Is that even legal? Um, if you don't want to, you could do something like, I mean, this is getting silly, but you can say like, or type of cache um, equals uh, list. Does this work? Yeah. I don't know. I don't know. I think in this case it's fine. I think in this case it's fine. Um, but this is a good place to ask a question. This is a good place to ask a question. Is it legal to adjust the test code? If not, maybe you could do something like this. It's a little bit hacky, but I think it's okay. If it were up to me, it would be okay. Like for example, like say you're working with a library, right? And you cannot. This is how the library passes caches. But maybe you have a better way to do a cache. So then you can do something like this. But this is one of those clever things that you definitely want to make a note of. This will overwrite the array cache and replace with a dictionary cache. So now I didn't overwrite the cache code, the test code, but I still have a working solution. If you did it on a sprint challenge, would it fly? Yeah, I think so. I think so. The test pass. I mean, I didn't. You know what I wouldn't recommend, and you know what I know people do this a lot. I wouldn't do like if n equals 50, return 10562230626642. If n equals 100, return this. If n equals 50, 500, return this. Right? That's a little bit iffy. Yes, you can pass all the tests just by pure brute force. I mean, that I don't think would fly, but something like this I think is totally fine, right? Something like this is still pretty clean. It's you want to make a note of it, but it's I think this is fine. Yeah, I think like why would I kind of prefer this over this one. Like Jonathan, I'm not saying your solution is bad, but like to me this is like even more clever, right? And I say clever in a worse way, in that I when I read this, like I have to look at this. I'm what is going on? Like what is this doing? Um, what is going on here? We're doing triple assignments. We're concatenating a list comprehension with a built-in cache. Like there's sort of multiple layers of cleverness here, right? Where here we just have like one little line of cleverness. So I don't know. Like this is just nitpicking, but I guess my takeaway is that I think this is fine. A little bit. Don't think, Michael. What is? Do you have a question, or is that a comment on my unscientific way of doing computer science, which is actually, I think, the real scientific way? or you're just having some frustration with this problem. Did we already say what the time complexity of the solution is? I think time complexity is O of n. While we have this cache, because we're only going to need to do one iteration of each to fill out each of these. Space complexity is going to be O of n as well, since we are one, we need to have space on the stack for this recursion, and then two, we need to have space in the cache, one entry for each number of n. So both time and space complexity of this are going to be O of n. Comment on brute force answering the tests. Yeah, and I mean, it's silly that we do have to say that, but I do know that when we look at endorsement interviews, that it is not beyond is not beyond students to do things like that in hopes that they will pass. You may pass the test, but that's not going to be something that you check into a code base. So that's why we do interviews with your TLs. That's why we do end of endorsement interviews with instructors after those tests as well. Why do you have the cache as an argument? Because we're saying here n is not in the cache. So if n is not in the cache, we need to make sure it's in the cache because we're returning that, right? So if like we're calling eating cookies of 20 and 20 is not there, this would return an error. But this is going to guarantee that we put it in the cache first before we return it. Without the cache, this is going to blow up to be something very, very, very bad. Something like 2 to the n power, or like 3 to the n power, something pretty awful. Remember, Fibonacci is golden ratio to the power of n. So this is going to be even worse because we have 3 instead of just 2 of these recursive calls. Oh, eating cookies and because we need to pass the cache along because we're slowly building up the cache. So we are we need to pass that along with our recursive function. Otherwise, the recursion is not going to have. See, it gets declared as a default argument as none. So if we pass it in like this, then we have no cache. Our cache is just initialized to none. Yeah, the cache is a little backpack. It's a good way to think about it. Yes. Okay. Good. Let's get to Slido. Is it fair to say that if you don't look at the test.py files, the problem might be impossible to solve? Yes. That is fair to say. That's part of understanding the problem is looking through everything you're given. It's not all going to be in the spec necessarily, but this is true of real life too. You need to look at that's what test-driven development is actually about, right? You write the tests, and then from the test, you can determine what the functionality should be. So this is absolutely accurate. Okay, I'm lost on how the cache stuff works. Are we going to go over this more? If not, do you know any resources that will help? Caching is a pretty simple concept. I think the implementation gets complicated, but basically, a cache is just saying any expensive calculation, if you're doing it more than once, you want to store the results, right? For example, if let's say we're doing like 5 times 5, right? That's a calculation. If you're let's say you don't memorize it, but you have to put out, okay, I have 5 baskets of 5 oranges, and you have to lay them out, and then you can count up, okay, I have 25 oranges. So instead of doing that every single time, you can just store that results in your cache, in your backpack, right? You write it down on a piece of paper, 5 times 5 equals 25. Now, next time you come across that calculation, you don't have to get your oranges out again. All you have to do is look in your cache to see if the result is there. I think for me, and maybe for most people, it's easier to think about it in terms of things like browsers, right? You know that browser caching works like when you go to a website, it'll download all the CSS or all the JavaScripts and all the images the first time, which takes a while. But after that first time, it's stored in your cache. So then you don't need to do server requests anymore. So I think if you remember that will help you. Anytime you're doing an expensive calculation more than once, you can speed up the performance by caching that result. If you have more specific questions about that, or if you have more points where you're lost, I think this will benefit you to go to try to ask some more questions. I think caching is a simple concept. Stuff like this can get hard. Again, the implementation of dynamic programming and memoization and things like that and tabulation, I think, is another word that I can never remember the difference between. But overall, the takeaway from caching is if you have an operation you do more than once, good to cache the results so you don't have to do those expensive calculations. Can you explain why the cache is needed here? Yes, key value pairs. All caches are going to be key value pairs. You need to have, like, why is all caching key value pairs? Because you need to know how to retrieve it, right? You need to have some description to identify what the problem is, and then you have the result. So that's the key, and that's the value. So if I were to come up with a key for my 5 times 5 example, my key would probably be like 5x5, right? And then I can look that up in my multiplication cache, and it will retrieve the results 25. Cache naming is a that's a subject that can get pretty deep, especially when you're doing things like browser caching or fragment caching, or other things like that come up in development, web development, mobile development, things like that. But n-1 is a key. So n, we are populating the cache here. So n is the key, but we're passing this in recursively. So we're passing in our same cache, but we're passing in our a different n, right? So then this n-1, when it gets called recursively, is just treated like n in the recursive function. Like this, anytime you run a function, it doesn't know if it was called from a main. It doesn't know if it was called recursively. It doesn't know if it was called from a terminal. All it knows is that it's passed in this n, it's passed in this cache, and it has to do all of this stuff with it. We'll save this this big O one for the end. We'll save some time for reviewing. Fair to say that any recursive function always returns a call of itself that's manipulated somehow. In the factorial example, return factorial times n-1. Yes, I do think this is fair to say, because you need to be moving towards your base case. If you're not moving towards your base case, or nothing is changing, or nothing is manipulated, then you're just going to loop forever, right? You're going to keep going on and on and on. So yes, you do need to be moving towards your base case with the recursive function. So I do think this is a fair assumption. What are the benefits or drawbacks using lists versus dictionaries for caching? The nice thing about dictionaries is that they have you can use arbitrary keys, whereas lists only allow you to do integer lists. Another that was a terrible sentence. Lists only allow you to do integer indexes, and in order to add something like, if you wanted to add a key of like 500, then you would need to have 500 items in your list, or actually 501 items because we start from 0. Whereas a dictionary, you can just store like a key of 500. So actually, I would always use a dictionary for cache. That's me. You can see by the built-in Git blames that I did not write these tests. So I mean, sometimes you got to work with what you got. But yeah, I think in general, like, arrays again are slightly more efficient than dictionaries, but you'll learn more about that when you get to data structures and then hash tables as well. Should all of the answers to the algorithms assignment be recursive? I forget, but I think most of them can be recursive. I think these are a lot of recursion practice. Of course, you can also solve them iteratively. But if you can get a solution, a recursive solution or an iterative solution, I think either are valid. Are iterative solutions always preferable to recursive ones due to space complexity? When is it more practical to use recursion? Is recursion just clever? Yes, yes. I would say that the advantages come when you come in terms of readability. Sometimes it's really intuitive to say that we do this thing and then we do it again and then we do it again and then we do it again. Sometimes it's really clear in recursion. Like I think that this is pretty clean code using recursion, right? And then it illustrates that pattern really well. where we have we take the previous one and then add a 1 in front. Then we take 2 previous and add a 2 in front, 3 previous and add a 3 in front. Like, this is pretty clean. I think you could do a similar thing with a for loop, but yeah, I think that I don't think you're wrong when you say that they are just clever. I lost this problem. Oh, yeah, I don't think you're wrong to say that recursion is just clever. But a very, very practical reason to learn this is because recursion does come up in job interviews and whiteboard interviews. So it's good to know what it is. It's good to know how it's applied. But it's also good to know the trade-offs. And I think that's something that you can talk about in your interviews. Can we go over the TK challenge from yesterday? Classify the runtimes of each of the following functions. Yeah, well, we're running up on break time. But yes, we'll definitely try to save some time to go through Big O. It seems like this, out of all the subjects, Big O is probably the one that is craving the most review. When studying algorithms to prep for interviews, are you just trying to study as many different problems as possible and learning the solutions ahead of time? Absolutely not. Absolutely not. In fact, I'm going to tell you now, you do not want to memorize these. That's not making a good use of, oh man, Slido. It's not making good use of the space in your brain. If you're going to memorize anything, I would say memorize them about your main language and your main track. Like, memorize the syntax of JavaScript, right? How do you add something to the start of a JavaScript array? How do you remove something? How do you use map, reduce, and filter? How do you do a callback? How do you manipulate the DOM, right? How do you start a React app? What is the React lifecycle? Like, those are the things you want to memorize. Don't memorize like, maybe I'll get this eating cookies problem, and if hopefully I do, so that I'll memorize it. The truth is there's an infinite number of possible algorithms. And actually, like, this eating cookies problem is more commonly known as counting steps. We just changed it to make it a little bit less easy to Google. But if you say, like, if you get a counting steps problem, but I don't know how to do counting steps, I only know how to do eating cookies, then I think you're missing the point. That's why we teach the problem-solving framework, right? We're not trying to teach you algorithms. We're trying to teach you the problem-solving framework. And I actually don't recommend that you memorize sorting algorithms either, even though those are more likely to come up. It's more important to memorize roughly how they work. Remember their complexities. Remember, like, is this an in-place sort or is this an out-of-place sort? Is this a O of n log n sort or is this an O of n squared sort? Those are more important than just memorizing the code. So yeah, don't memorize this stuff. Just get practice with the problem-solving framework. You still want to do as many different algorithms as you can, but just that's more for getting practice with the Ooper framework, with solving different kinds of problems than memorizing the actual code. Next. Is there a difference between caching and memoization? Memoization is a form of caching. Caching is not. Caching is the broad general term. Memoization is a specific type of caching in recursion. You can Google that. Memoization is a optimization technique used to speed up computer programs by storing the results of cached results. Yeah, this is the thing I always forget. So memoization is top down, whereas dynamic programming is bottom up. And then there's also a thing, tabulation, which I also forget. We don't say anything else here. Tabulation, dynamic. These are all different kinds of caching, but you can read the details here. I don't think that's too important to remember either. That's pretty esoteric, but the idea of caching is the bigger takeaway. Where are we? Can you solve random dynamic programming problems that you've never solved before on Friday during Q&A? We can look at one. I can try to find one. But I mean, if you have dynamic programming is an optimization step, right? So you don't really solve things using dynamic programming. You solve it and then you optimize using this technique. So it's not, I don't think there are any dynamic programming problems. There are things like Fibonacci, which can be solved and then optimized using dynamic programming. So maybe that's something we can take a look at. When solving on HackerRank, where you can't see the test cases, how would you go about solving something when only some of the test cases pass? This is a really good question. On HackerRank, you're, just like I said with these problems, you're guaranteed to have all of the information that you need to solve the problems. Like, these have been tested with users. It is possible. Now, if there's a hidden test case, you should maybe be able to figure it out. Being able to test your own code, being able to come up with good test cases, good coverage is a skill as well. So that's something that you'll need practice with. That's something you'll need practice with. What do you do if only some of the test cases pass? Try to figure out which are the ones that break. Try to look at your code. Try to do edge cases, right? That will help you identify these things. But you should have all the information that you need. Again, sometimes it's in the spec, sometimes it's in the provided test, sometimes it's the provided code. You should have all the information you need. How important is speed when going through the problem-solving framework? I'm not going to say it's unimportant, but I would say that right now speed is not something that you should necessarily focus on. It's important when you get to whiteboard interviews because you have a limited amount of time. Like, if you have 30 minutes to solve a whiteboard interview, you don't want to spend 25 minutes on step one, right? You leave time for each one. In a 30-minute interview, I do like to spend at least a bare minimum of 5 minutes understanding the problem. And that includes talking through it with my interviewer. So they give the problem, I talk it through. It's like, okay, here's my understanding. So if I have it right, this is, if I do this, it should return this. Okay, what about this? What about this? Ask questions. Okay, interesting. So is it like this? And then if you're wrong, they'll say, no, actually, it's like this, right? It should be a dialogue before you even uncap that pen. You should be having that conversation. Now, 5 minutes seems like a long time, but after that, then you do want to start writing, right? You do want to come up with a plan. You do want to make sure that you leave yourself enough time to code, and not just code, but to debug and to improve your solution once you get there. So again, for whiteboard interviews, I would say 5 minutes is a good rule of thumb to spend on understanding the problem. But then you want to get a move on. But for right now, I would say don't focus on speed. Focus on getting that understanding. Does not dynamic programming just mean using recursion? Dynamic programming is a form of caching that is recursion. Okay, so this is a better definition than I have. Dynamic programming is a technique for solving problems of a recursive nature, iteratively, and is applicable when the computations of the subproblems overlap. Okay, I don't know if that's a better question, but dynamic programming is a form of caching that is very, very specific. Top down, or bottom up. Wait, top down dynamic programming. Yeah, dynamic programming is just a form of caching that's used for recursive problems. I think that's as simple of a definition as I have. Okay. Pass the cache. Okay, TK explains caching well. Awesome. Previous recording with Artem. So yeah, Artem's a part-time contractor. So yeah, different perspectives can give good other results. I think there's some previous recordings in TK. So yeah. Is memoization a real word? Yes, it is. I think it does come from memorize, but I don't know why they dropped the R. Printing functions inputs. Yeah, printing. Oh yeah, this is a good tip. This is a really good practical tip. Print the inputs, and this will help you with HackerRank to see what the tests are. Yeah, memoization. That is the correct pronunciation and spelling. I'm not just dropping the R as a verbal tick. Okay, we are over time for a break, so let's take that 10 minutes. And when we come back, we'll take a look at the anagrams problem, and then we'll leave some time for Q&A and review. That was 10 minutes, so come on back. Yes, I did build this. I think I showed this during last week's Q&A. But one thing that's, well, when I first moved to Cleveland, I'll show you my GitHub. This is something I'm quite proud of. When I first moved to Cleveland from the Bay Area, okay, which was in 2016. So this is when I left the Bay. This is when I was moving. I wanted a project that would keep my green squares up. So I decided to make a game every week. You can see I started here. A lot of these were pretty terrible, but one of them happens to be fun, kind of by accident. That was this week 26 game. I updated it with music. So the music procedurally, not procedurally, the music will build up as you progress into the game. And then I ended up really liking it. I was addicted to my own game, so I thought it was actually worth it to stop this and to just work on getting this out on mobile. I mean, it's kind of funny that if you look at what the original game looks like, it's very, very, very similar to what it is now, except for yeah, it took me 1 weekend to basically build the game, and then I've spent like 2 years building all the infrastructure and UI and back end and everything around it. But I mean, the nice thing is it was a fun project for me to keep my green squares up. Then I got hired at Lambda School, and you can see it was a little bit less consistent. But a lot of that is because my primary role here is not as a developer. It is as a coder. So I do go through periods where I'm very focused on other things, and I haven't been coding as much. But I have a job now, so I'm not as desperate to keep those green squares there. But for you all, if you're looking for good projects to work on, if you're like me and you like games, I think games are a fun way to keep those green squares up. If you're not interested in games, find something that you are interested in and use that to keep yourself motivated. There's a lot of algorithms. I wish maybe I could do a brown bag or something sometime. I don't know. But there's a ton of algorithms and complexity and object-oriented programming and all of the things that we're talking about here. I've been able to use in this project. So I think I'm pretty proud of it. Now it's still a work in progress. I still have a lot of work to do, and I have a lot of crazy features in my head that are kind of half baked. But yeah, this is what I like to do for fun and on my weekends. Yeah, there's mud. The technology behind the mud, a lot of it comes from the stuff that we were doing. Oh, okay. Yeah, actually, that's jumping ahead. But yeah, the mud you created in week 1, you're going to be building on that for your build weeks. And then that technology, a lot of that came from the work that I did building my own game, right? And it's in production. It's free on iOS and Android if anyone wants to give it a shot. It's very lightweight, very small, low power. It's intentionally like perma dark mode. So it doesn't use too much bandwidth, doesn't use too much data, doesn't use too much battery or anything like that. Should work on the oldest of phones. I'm testing on a 4.6 Jelly Bean Android phone, which if there's any Android people here, you know that's practically a relic. So yeah, that's Godai. Also related to the elements, I'm super into the four elements. So whoever posted the Uncle Iroh avatar reference, very close to my heart. Okay. So the problem, getting back into our problem for today, and we're running a little bit short on time. So I want to make sure we get into this. Here's an algorithm. Given a word, return all the anagrams of that word in the English language. So I want to go through this problem with you all. And I want to go through the Uber problem solving process. So step 1, understand the problem. First step is, what is an anagram? What is an anagram? Maybe that's your question. To answer that question, an anagram, you can Google it. Actually, let's Google it. Anagram definition. An anagram is a word, phrase, or name formed by rearranging the letters of another, such as cinema forms the word Iceman. Okay, cool. So it looks like we need to take an anagram we want to take a word, and we want to return all of the words that have the same letters, both counts and the letters themselves. Okay. What else? What else do we need? If I were to give you this as a whiteboard problem, what questions would you ask? What do we need? Do we have everything we need here? How would you approach this? A dictionary of the word kind. Can you use libraries? How do you get the dict? Yes, you do need a word list. So great question. So let's fetch that word list here. Yes, here's my anagrams file. So the nice thing about I have a Unix machine is that there's a built-in word list, which is I think CP user share dict words to here, and we'll call it words.txt. Now we can open it up and see we have a word list. Okay, so here is our list. We can see there is 235,886 words in this list. Okay, what else? What's next? Yes, this is definitely a trend. This is also a trend. This is another thing that students get upset about. Like, hey, you're supposed to know this stuff. Like, you shouldn't be using Wikipedia and you shouldn't be using Google. That's a part of every programmer's life. Again, like, why memorize it when you can just find it on Google? Now, there are some things that you can't Google, so you want to practice. You don't want that to be your only solution, but when available, use the tools you've got. Okay, start doing the logic, 26 letters in the alphabet, etc. Okay, so we need to pull that in. So I think we know what an anagram is. Let's jump into our plan. What is our plan? First, we need to start splitting those strings. I think what you mean is you want to pull this into some kind of data structure, right? So we want to read this into our program. So we can do that using our file opening code. So we have, let me see. I want to actually open this so I don't waste time. But I lost that code here. I think it's in this one. F dot open. Here we go. So F equals open words.txt. We want to make it read. Words, let's call it word list, equals f.read. And as you mentioned, split those strings. We know that they're separated by new line characters, so we can do dot split /n. And that will give us word list. It will give us this long list here. Okay, what else? Merge sort. Merge sort. Okay, let's keep that in mind. What do you? Okay, and also I want to just throw this out. This is a pretty classic problem. This is a pretty well-known problem. So if you do know the solution off the top of your head, don't just blurt out the optimal solution. Let's try to go through the problem-solving framework. What is the difference between doing a split and indicating a delimiter? This split, the split will. The splits. If you don't do this, I think it'll just split on space. I think it'll split on the space character, if I remember correctly. But this is saying we want to split explicitly on this new line character. Yes, something like if letters in word equals another word or something. Yeah, okay, so we want to determine how two words are not algorithms, anagrams. So what would be the algorithm for that, right? Because the easy solution would be given a word, check each other word in the lists, and return all that are anagrams, right? So we want to have a function to determine if two words are anagrams. So here's a basic list. Here's a basic algorithm. But in order to do that, how do we know if two words are anagrams? How do we know if two words are anagrams of each other? And lowercase all the dictionary words. That's a good one. Let's call this word list equals w dot lower for w in word list. This will give us, and we can also say if len words is greater than 0. This will give us, we should get rid of these capital Z's. We also want to get rid of this empty one. Looks good. We're all lowercase. Yes, you're correct that I think we want to lower all of these. Loop through each word at each index and check that that letter is in the current word. So something like, for each letter in the first word, check if that letter is, check if the letter matches the same position in the second word. If you get to the end, it's return true. Yes, we also need to check the length, right? So maybe say like if word 1, if length of words are not equal, return false. If it doesn't, return false. If you get to the end of the word, return true. Same length, all the letters in the first word are present at the same frequency in the second word. Yes, okay. This is, Matthew, I think if you have all the letters in the first word present at the same frequency, that will also do the same length. So maybe, I mean, I think it's okay to have this here, but I think you might be getting at an optimization. So I think this will work. I think this will work. Given a word, check each other word in the list and return all that are anagrams. How do we know if the two words are anagrams of each other? Okay, we do this. We run this is anagram function. Is anagram. Let's call this word 1, word 2. So we can say something like if len word 1 is not equal to len words 2, return false for letter in word 1. I guess we want to do range, right? So we can say for I in range len word 1. If word 1 of I is not equal to words 2 of I, return false. That's this. If we get to the end, we can return true. That's not going to check if the letter is the same. Oh, you're right. Okay, so how do we do this? Okay, so this is wrong. So my algorithm is totally wrong. This algorithm is totally wrong. Position doesn't matter. So how do we do this? How would we go about this? Yeah, I don't know what I'm thinking. I guess my brain is not working. So let's get rid of this. Yes, back to the planning stage. Okay, so how would we check if this is an anagram? If word I in word 1, I in word 2. Okay, so so what if we have like A, B, and A, B, B, right? Then we're gonna go through A, check if A is in there. Yes. Check if A is in there. Yes. Check if B is in there. Yes. But AAB is not an anagram of ABB, right? Okay, then remove the found match from word 2. Okay, that could work. So we can say for letter in word 1, let's call this letter list equals list of words 2. This is taking a word like ABC and turning it into a list. So lists of ABC gives us this. So we can say, actually, why don't we turn this into a list 2? Word 1. If letter in words in letter list, and we remove, how do I remove something? I think it's just straight up remove. Letter list dot remove letter. Right? We can use dir. Insert, yep. I think it's just remove. And I think that will help list dot remove. Remove is the first occurrence of the value. Cool. Not letter. Else return false. And if we get to the end, then we can return true. That work? Let's try this. Is anagram, what is it? Cinema and Iceman. Should return true. Cool, that looks good. What about ice map? Should return false. All right, so far so good. Is using remove optimal or shooting for a quick first pass? Yes, we're just shooting for a quick first pass. So what we want to do here now, if we can fill this out, right? We can say for words in word list, if let's say anagrams equals this, for word in word list, if is anagram of word and whoops, what should we call this? Just call this W. These are not good. These are not good variable names, but first pass is okay. If is anagram, anagrams dot append W, and then we return anagrams, right? So let's try this. Okay, let's try anagrams of Iceman. Anemic, cinema, Iceman. Cool. I guess we can also say or word one. I guess is a word an anagram of itself? Maybe we and W is not equal to word. Anagrams of Iceman. Okay, that's better. Okay, now again, we're running a little bit short on time, so we have a working solution, but I don't know if you could tell. I don't know if you could tell here, but there was a little bit of lag, right? Maybe we could run a timing test, but I think this is taking like a fifth of a second, right? I think we can do better than that. We can actually do some complexity analysis. We can do some, so I guess actually that's a good, since we wanted to cover big O, what is the time complexity of this and what is the space complexity of this solution? We have a working solution. This is a good first pass. What is the time complexity? What is the space complexity? Of n squared for the time. What is n in this case, Jeremy? And how did you get that? Length of what? Length of the word? Length of the word list? Something else, something I think is helpful is there's no answer. There's no one right answer. It's not like it's not like math where like 5 plus 5 is always 10. Complexity is language. This is a way of describing code. So it's not enough to just say like O of n squared. You have to say O of n squared where n equals this. I mean, justifiably, you can say this is constant because the length of our word list is always going to be constant. But this is more of a language for describing code, right? Not an exact mathematical answer. O of n, because the runtime is dependent on the input size. Kyle, what is n in this analysis? Okay, so Scott says n is the word list length. Okay, so yes. So we can say that it's O of n for, we have to do this. We have to go through each word, right? And then we can also say that for this we have maybe W, where W is the length of the word. But is there a way to, so okay, let's write that down. Time complexity is O of n. N is the length of the word list. Space complexity, I guess we can call also O of n, but maybe not. Like let's assume that this is just the word list we're given, so we don't need to copy this. We'll say space complexity is actually O of 1. Is O of 1 because we're asking that we're given this, right? So we're not using any extra space. That's how I'm choosing to define it. Complexity is not, it's not an estimation, but it is like there is some precision to it, but it's more like describing the shape of something. That's how I would put it. You're describing the shape of something. Now you can look at it from different angles. You can say, but in general, I don't know how to answer that. I wouldn't say it's an estimation, but I would say it is not. It's not an exact. Like it's not like you cannot look at this code and definitively say like, this is O of n. That is the only way you can say it. Like you can say, you will have to say O of n where n is the length of the word list or something along those lines. I wish I had a better example. I wish I had a better example of something that would change that. I mean, actually, I do have a better example, but I have a great example. From the training kit, I forget who, but someone pointed out a something that was n squared in this training kit, but it was actually, I would say, O of n. I don't know exactly where that is. Or was it O of n squared? I can't find it now. But yeah, there's a I think it's in training kit fixes. You can see it. Anyway, you have two loops. Yes. So Kyle, yes. So you're looking at this, right? So you're saying there's a for loop and a for loop. Yes. So what you could say, but this is not going through every letter in the word list, right? So you can say O of n times W, where n is the length of the word list, W is the length of the word, right? So this is also accurate. This is also accurate to say, because if you have a longer word, you're going to have to go through more in the for loop. But what you also might say is that because the length of a word is going to be very, very small compared to the length of the word list, like if you look in here, we have 235,000 words here, whereas the longest word is probably going to be like, how long is this? 20 letters. So it's going to be much, much smaller compared to that. So this is accurate. Also saying O of n is accurate, where n is the length of the word list. Both are correct, but you need to have this justification here, right? Okay, great. That was a perfect example. Yeah, and Leslie, you're also right that that when we talk about big O, we often mean the worst case, or you can mean the worst case or the average case. There's big theta and big omega, which are being more precise. But in general, we just talk about it as if we just refer to all of them as big O. Yes, that was what I was referring to. So this is, you could call it something, you could refer to it like like this. Like I wouldn't call this n squared. I would call this like n, wait, n to the power of c. That seems, anyway, yeah, there can be multiple right answers, but you do need to justify this. All right, so if we know this, is there a way to improve this? How might we improve this, this complexity? You're not, if you say this, you need to say what n is. Okay, that's something that I always want. You can say that, and it can be accurate. Like I would say, saying something like this is accurate. Like this is indisputably accurate. Like this is not an estimation. This is not an opinion. This is accurate. But what I mean is that you can't just say this is O of n done, right? You have to say O of n where n is the length of the word list. But this is also right. You can say O of n times W, where n is the length of the word list and W is the length of the word. Both of these are correct, but both of these, you need to have this, this additional sentence after this. O of 1, O of 1 is, I mean, O of 1, there's no n there, right? So you can say that this operates in constant space. But maybe we do need to add the caveat that we're not including the dictionary in our word list. Yeah, exactly. So you need to make your case why this is true. Well, what I want to say is that you need to say what n is in the case, because it could be different things. It could be the length of the word list. It could be the length of the word. It could be many different things. It could be the length of the two words put together, right? But you need to specify what each thing is. That's what I mean by it's not an exact answer. How can it be O of n? So what I'm saying is that there is an argument to be made that W is going to be so small compared to n. Like the maximum, what is the maximum word length in this list? It's probably going to be like, again, I'm estimating to say it's like 25, right? But 25 is going to be so small compared to 230,000 that we can actually just treat it as constant, that it doesn't really come into our complexity evaluation. Okay, can you think of any ways to optimize this? I think a few people were hinting at a way we might figure this out, or we might have a better way of solving this in a more efficient time than O of n. Actually, I propose that we can solve this in constant time. We can actually solve this in constant time. We can get this down to time complexity of O of 1. Binary search the word list instead of searching through the entire list each time. Michael, what would you be searching for? Yes, Allison. Yes, sort the words first. Allison, you're right on. You're right on. So how would we do that? Cache anagrams with a set of letters as the key. Yes, Scott, that's close. That's close. What I think if you combine these two, so sort the words and use that as the key, and I think that we're on the right track. So here, I'm just going to go through this quickly, and then we'll spend a few minutes at the end just talking through a bit more complexity. So what I want to do is I want to pre-process this instead of putting them in a word. I actually want to put it in a set. So actually, let's do this. Let's say anagram cache equals this. For word in words, we can say we'll create a signature equals so what I want to do is I want to redefine this. This is anagram thing to say that two words are anagrams if they have the same signature. The same signature means that we sort the words. We sort the letters in the words. So something like cinema signature would be A, C, E, I, M, N, right? So this is the signature. Iceman has the same signature. A, C, E, I, M, N. Right, so two words are the same if they have the same signature. So we're going to use this as the key to our dictionary. So we can do that with dot join sorted words dot lower. I guess we already lowercased it. Then we can say if signature not in anagram cache, signature, anagrams cache of signature equals word, else anagram cache of signature dot append word. Words is not defined, this should be word list. Okay, now if we look at our cache, you can see, okay, this is not great, but let's check our signature here. Let's check our Iceman Cinema. Anagram cache of, what was it, ACE IMN? ACE IMN is Anemic Cinema and Iceman. Okay, so cool. So now all we have to do is look it up in our cache, right? We pre-process it. We pre-process it once, and now we can fetch all of our anagrams in near constant time. All we need to do is sort these words. So the time complexity of that will be like if we want to find all the anagrams of of cats, right? We need to sort cats. Will be ACT, and now we can fetch it in constant time. Why store the strings as a list when a string is technically an array? No need for the nesting. Which nesting are you talking about? Do you mean storing the words in a list versus just having a string? That's just so for easy appending. Okay, so I'll leave it to you as an exercise to fill out the rest of this. But yeah, it is possible, and I guess I can also copy paste the solution. But I'll drop this in for you right now. Anagrams.py. Note that this won't work if you just copy paste it, but there's some good pieces in here that you can work out. So again, what are some ways we optimize this? We sorted the word, right? Knowing about sorting can be very powerful. We use the right data structure. You'll learn more about the costs and benefits of data structures, but you might remember that caches or dictionaries are really, really quick. So this gives us O of n. This gives us O of 1 searches, but it takes O of n space, right? We need to have all of our anagrams in this cache. So this is actually going to take O of n space. So we're a little bit less efficient in terms of space, but we're more efficient in terms of time. In this case, I think that it's much more efficient to use that trade-off of space for time. Okay, let's see. What are our questions? Can we look over the TK challenge from yesterday? Sure. So that should be here, right? These are new to me as well, so I am not sure what these are. But let's yeah, we can take a look at these. Okay, constant time. This is constant. Actually, I want to use my own code. It's this one, right? Big O. So we have all of this code. Let's do our animals here. And what was the other question? Is how do you calculate big O? Maybe it's better to just look at this. This is constant time because it doesn't matter how big the input is, how small it is. All we're doing is a single operation, right? Here, this is logarithmic because each time we're dividing by 2. That's a good sign that you're doing logarithms. This is linear. You have the for loop, right? For each item in your input, you're doing one thing. So that's O of n. N log n is merge sort. This is hard to describe. I think O of n log n's are the hardest to describe. But basically, you need to, the way I think about it is that when you're sorting something, you're you take a unsorted list and you need to put it in the right place. You need to find the right place for it. So you need to do that for n items. And finding out where the correct place is roughly log n. That's just how I think about n log n. Polynomial time. This is, yeah, I think this is, this one's not right. Exponential time. These are, yeah, this is like our Fibonacci, very, very slow. Permutations are very slow as well. So if we look here at our code, we can see some more examples. Again, this is O1 because no matter how big the list is, no matter how small it is, all we're doing is returning these, returning the list itself, or more accurately, a pointer to the start of the list. I spelled that wrong. Right? How do you know what the time complexity is for recursion? You need to think, how many steps does it take to get to the base case? Okay, here's another one. Count animals. Count animals, num animals equals 0. For animal and animals, num animals plus equals 1. Right, so we're going through each animal. We're increasing our counter by 1. If we have 10 animals, we'll need to do this 10 times. If we have 100 animals, we'll need to do this 100 times, and so on. Same for get lowercase animal. We go through each animal and we do something, right? In this case, making a lowercase. We have this for loop here that will do that iteration. Same thing here. This is a search. This is our linear search, which we know is O of n. Here's another linear search, which is O of n. And our shuffle, which we talked about with Fisher-Yates, is also O of n. O of n squared. Here's O of n squared, where we here's O of n squared, where we will go through each animal, match them up with each other animal. So this is a nested for loop. As we saw, having a for loop in a for loop often means that you're doing n squareds, but look at what you're going through. Look at what you're going through. Like, for example, if we had a for loop in a for loop, but we were saying like let's say we just had 3 different exhibits, right? Exhibit 1, exhibit 2, and exhibit 3. This looks like a for loop in a for loop, but this is actually going to be O of n. Do you see why? So this is like, we can put a duck in exhibit 1, duck in exhibit 2, duck in exhibit 3. The reason is that so we're doing 30 things here because we have 10 animals. If we doubled the number of animals, we're going to double the number of operations. This number, this 1, 2, 3, is going to stay constant. I mean, this is terrible naming. It should be like num, right? But just because we have a for loop in a for loop does not make it n squared by default. It's only n squared if you're going through the same collection. This is, I think, the biggest stumbling points that people come across. They just remember, oh, for loop in a for loop is always n squared. Not always. It depends what the collection is, right? This is n. If this is n and this is also n, then you have an n squared. If this is n and this is constant, like if we did this 1, 2, 3, then this is going to be O of n. Does that make sense? Okay, let's see if we can take a look at these. Classify the runtimes of each of these solutions. Square roots. So we're just doing a square roots. That's going to be constant. Pretty much all arithmetic operations are constant. For I in range 0 to square root, we print the I. So this, I would say the time complexity is O of the square root of n. Here, def bar of x for I in range 0 to 1, 4, 6, 3. This is the same thing. This is the tricky, this makes you think that is going to be O of n because you have a for loop and a for loop and a for loop, or O of n cubed. But this is going to be constant, right? Meaning if we double it, we're not going to double the amount of times. If we double the size of x, we're not doubling this, right? But we have for j in range 0 to x, so this is going to be an O of n. And for k in range x to x plus 15, and this is going to be constant as well. So I think this is going to be O of x, I should say. This one is going to be O of x. So even though you have triple nested for loops, this is the only one that's actually iterating based on the size of n. This is always going to loop 1, 4, 6, 3 times no matter what. This is always going to loop only 15 times no matter what. So even though these look like very big numbers, this is still going to be O of just O of n, where n equals x. You could just say O of x. Does that make sense? I see I only have like three people on my screen, so I see like one person nodding. So I know that at least one person gets it. I don't know about the other 120 of you. Okay, two people got it. Better than nothing. Okay, and this last one, copy this. Midpoint equals this. For I in range from 0 to midpoint, we print out the array. For underscore in range 1,000, print high. So I think this is going to be O of n as well, right? Where we just, even though we're going through only half of these items, that's still going to be like n over 2. This one doesn't do anything. This just prints high 1,000 times. Doesn't matter if we increase array length by double or by half, this is still going to print the same number of times. So even though these numbers are big, and even though this number is halved, this is still going to be O of n. Okay, we're out of time. I don't want to hold you up. I'm okay to go through a couple more examples. Do we have, or ask any more questions? Are there any questions about, okay, Slido is good. How do you calculate these? The way you calculate these is just go line by line and identify what the time complexity of each line is. So I look at this, I say this is O of 1. Okay, I look at this, I can see that this is O of n, where n is the square root of n. So that was confusing. This is O of n, where n is the square root. Here I'm looking at this. Okay, this is constant. This is constant. This is constant. This is constant. Here we have a for loop, so this is O of n. This is constant, and this is constant. So I know that I have an O of n. If something is after it, then you add it together. If something is nested within, you multiply it. So that's why when we have a for loop and a for loop, you can get n squared, because that's n times n. All right, any other questions? Say it again, the last part. Okay, go line by line through your code. Identify the time complexity of each item. So what's a good example? So if I'm looking at this, shuffle animals, I'll look at this line. Count animals. What is count animals? Count animals is going to be O of n. O of n. This for loop is going to be O of n. Also, we have stuff in here, right? Random.rand range. This is going to be O of 1. O of 1. This is going to be O of 1. This is going to be O of 1. This is going to be O of 1. Right? You don't need to write all of them out, but just go line by line, figure out what the complexity of each of these are. If they're sequential, you add them together. If they're nested, then you multiply them together. So here, this is going to be O of n. This for loop is O of n, right? O of n. The second for loop is O of n as well, and this print is going to be O of 1. So since these O of n's are sequential, so you add them together. So this is like O of 2n, which is just O of n. These are nested, so you multiply them together. So you do n times 1, which is O of n squared. If you divide, it's a log n, only if you divide each time. So here we're dividing in half, right? But we're not dividing each time. We just divide it once. So this is just printing out the first half of the array. This is not actually doing a repeated cuts. So just dividing. If every time you iterate, you reduce the input size by half, then you have a log n. I think binary search is the easiest example of that. But if you just divide once, that's going to be, this is still going to be an O of n, right? And this is a constant. The difference between calculating time and space, that's a good, just, they're very similar. They're often very similar. If you think about, think about the data structures you're using, or think about how much memory you're using. So here we're not really using any extra memory, right? We're not declaring any new variables. So this, I think, would be O of 1 space complexity. Here we're creating a new list. So same thing, right? This is going to be O of n. This is going to be O of 1. This is going to be, this is a for loop, so this is not actually declaring any new memory. So this is going to be O of 0. Here we're using our original array, so this is O of 0, O of 0, O of 0. So we can just add up O of n plus O of 1. For space, if you're making a new copy of something or not, right? So your recursion is C times O of n. Yeah, if you're making a new copy, then yeah, exactly. So we're using extra space here because we made a whole copy of our animal list, and then we made that lowercase. If you go back to our eating cookies example, we had this cache, right? This cache is some extra space. So we need to fill this up with n items. So this is also going to be O of n because our cache takes up n space. If we did it without a cache, we would be O of 1 because we're not creating any new data structures. Yeah, recursion in general, well, recursion also takes up space because this is one of those weird ones where every time you do another call, you're also declaring that space on the stack. But that's a little bit trickier. It's a little bit harder to see because you're not declaring like a new list or anything like that. But yeah, that's a good thing to remember. Yeah, this is one of the trickiest things, space complexity as it relates to recursion. But once you get into computer architecture and you build it yourself, and that's sort of the theme with all these data structures. Like we're going to have you rebuild these things from the very fundamentals, and that way, like when you build it, you'll remember how it works. That's the big idea there. Is there something you should review? Is there material? I think there's some good material on Training Kit. If not, you can look at other old lectures. And if not, I think there's a lot of good stuff on YouTube, like time and space complexity. I don't know. I haven't looked at this, but it seems like a good 11 minutes primer. Maybe you can say like tutorial. See if there's any good things here. I think these are problems, not courses. What does space complexity mean? So I don't know. And you can also ask your TLs. You can also drop questions in the help channel. You can also, yeah, there's many resources you can use to figure these things out. I forget if, again, like this stuff has changed, so I'm not too, I don't know exactly what is in the training kit, but I think there's a lot of good stuff here. But again, I think the best way to do this will be asking questions. Okay. Any last minute questions? Again, sorry for running over time. But hopefully this was useful. Can we go over number 1 again? Number 1 of which one? Number 1, this question, the TK challenge from yesterday. I'm not sure what there is to go over it besides repeating it. But if you have any questions about, aside from this one, which I think is this polynomial one isn't accurate, I think the rest of these are should make sense. Oh, the O square root of n. Sure. Yeah. So how many times are we doing this thing? Right. This for loop, we're going to do something n times, and then where n is equal to the square root. So if n is like 25, right, the square root of 25 is 5. So we're going to loop 5 times. If n is 81, then the square root of n is going to be 9. So we do this 9 times. So the square, so I would classify this time complexity as O of root n. Basically, we loop as many times as this number is. Is it linear given the square root? Yeah, yep, exactly right. So this is linear given the square root. So this is like O of n, where n equals the square root of n, which is very confusing. But it would make more sense if this is like x or something. They're all linear? Yeah. I think that is accurate. Yeah, I think these are all O of n. I would call all, except for this one, O of square root of n. But this is O of n, this is O of n. So it's O of n, but not linear. O of n is the same as linear. O of n is the same as linear. This one is O of square root of n, which I don't even know what to call that. But it's better than O of n. This is because, yeah, like when this is 400, right? You loop through 20 times. So it's going to be better than O of n. Whereas this one is always going to be, when you double x, when you double the number x, you're going to double the amount of iterations you do. Even though that number is going to be very, very large, it's going to be 1463 times 15 times n. 1463 times 15 is constant, so it's still O of n. Yes, yep. And again, you want to be clear. I mean, these are easier because they give you this, but like you would want to say O of n, where n is the length of this array, for example. All right. Any other questions? I see people typing. The anticipation is always palpable. Okay. If log is the anti-exponent, is an O of square root of n the same as log? I think there are inverses in different ways. I mean, maybe inverse is the wrong word, but that's just how I think about it. I mean, square roots are actually exponents themselves, right? Because like square root of n is the same as 2 to the power of 1 over 2, right? So I guess they're both inverses in different ways. I mean, I would say it's the difference between like flipping the negative sign versus like adding. Anyway, yeah, I think this is. I think whatever helps you to think about them. Whatever helps you remember logs. I don't know if saying it's the anti-exponent is accurate or the inverse, like I said, but that's how I tend to think about it. You divided each step. Are you talking about this one? Are you talking about? Oh, here. Yes, this is like you divided each step, whereas exponents are you multiplied each step. This is like multiplying by the inverse, or like exponenting by the inverse. So I think they're similar in different ways. I don't know. I think that sentence is not making sense. Uh, I think if you're asking this, then you do understand what logs are and what square roots are. But so if you have more questions about how they work, I think you can ask. But I think I'm losing verbal capabilities, which I think means that it's about time to wrap up. So if you have any questions, go ahead and ask. Otherwise, meet with your TLs, meet with your stand-up group. Sprint challenge tomorrow at 8 a.m. like normal, 8 to 11, and then at 12 o'clock. I'll be hosting an AMA where you can ask all the questions you want about anything. So with that, good luck, and I'll see you tomorrow.